So in this video lecture, we are going to talk about interrupts, storage structure and input-output structure. To start with the interrupts is nothing but the signals that are given to the processor in order to indicate that a particular event has occurred. Different classes of interrupts are as follows. One is program interrupts. So interrupts that occur during the execution of program, those interrupts comes under program interrupts. And timer interrupts means if for the execution of a particular event, if a timer is already set and if the timer expires, so it has to indicate that the timer has expired. So in such kinds of classification of interrupts comes under timer interrupts. And whenever a read or write operation has to be carried out, for that, input or the output device has to be serviced accordingly. So such interrupts comes under input-output interrupts. And if the hardware fails, so in that case, the interrupt has to be issued to the hardware devices. So such interrupts are classified as hardware failure interrupts. Then moving on to the interrupt cycle, to start with, so whenever instruction has to be executed, first the instruction will be stored in the main memory, and from the memory it has to be fetched and it has to be given to the execution unit for execution. And during the execution of instruction, obviously, if any interrupt has to be serviced, then the corresponding interrupt handler has to be executed. So such stage are referred to as interrupt stage. So during the execution of instruction, if the interrupt is enabled, a corresponding interrupt handler has to be called and which will be servicing the interrupt. And suppose if during the execution of instruction, if the interrupts are disabled, then the normal fetching the next instruction, executing the instruction, that cycle will be carried out. So that is clearly being depicted in this diagram about the fetch stage, execute stage, and the interrupt stage. Then, so in this diagram, so sequence of events in processes, hardware and software is clearly being depicted. So moving on to the hardware part. So device controller or other system hardware will be issuing an interrupt. So once if the interrupt is being issued by the device controller or other hardware devices, the processor will be executing the instruction. So it finishes the current execution of instruction, and the processor will signal that it has received the interrupt by sending the acknowledgement signal. And after sending the acknowledgement signal that it receives the interrupt, it has to resume its execution after the interrupt is serviced. So for that, it will push the program status word and the program counter onto the control stack. The control stack is nothing but the portion in the memory, okay, which will be in which the program status word of the currently executed instruction and the program counter. Obviously, we know that program counter is a register that holds the address of next instruction to be executed. Since, as I told you that once if the interrupt has been serviced, the processor has to resume its execution from where it stopped. So for that, the address of next instruction will be stored in the program counter, and the status of the process or the status of the program will be stored in this program status word. So the content of program status word register and the content of program counter will be loaded into the control stack. Then after loading these registers value, the processor will load the new program counter value based on the interrupt. So in order to service a particular interrupt, the address of the interrupt handler will be loaded as a new value into new program counter. Then on the software side, it will be saving the reminder of the process state information. Then the interrupt will be processed and restoring of the process state information from the control stack and restore the old PSW and PC after the interrupt is being serviced. So this is about the interrupt processing, wherein which the sequence of events in the processes hardware and software is being clearly depicted. Then, so in this diagram, the interrupt driven input output cycle is being depicted here. The first step is the device driver will be initiating the input-output operation to be carried out. The CPU executing checks for the interrupts between the instructions. So CPU, which is in the process of executing the instruction, it will be often checking whether any interrupts are being have to be serviced. So in that case, if the CPU receives the interrupt, it will transfer the control to the interrupt handler. It will be transferring control to the interrupt handler. So first step is the device driver initiates the input output. And once if the input output operation is being initiated, the and the input is ready and the output is being completed, or the error generates the interrupt signal. So if the input is ready and the output is complete, and if the interrupt signal is being generated, then obviously the CPU will be receiving the particular interrupt signal, so that the transfer will be controlled to the interrupt handler routine. The interrupt handler will be processing the data returns from the interrupt, and CPU will resume the processing of the interrupt task. So this is about the interrupt driven input output cycle. So input output controller will be taking care of initiating the input output and generating, if any interrupt occurs, it will generate the interrupt signal and it will pass the signal to the CPU, so that the CPU will call the interrupt handler in order to process the interrupt. Moving on to the types of interrupts. The previous slide we have seen about the classes of interrupts as program interrupts, timer interrupts, hardware failure interrupts, and so on. And to talk about the types of interrupts, there are generally two types of interrupts. One about the non-maskable interrupts and maskable interrupts. So non-maskable means the interrupts that cannot be masked, or that cannot be neglected, or that cannot be ignored. Those interrupts are referred to as non-maskable interrupts. So they are reserved for events such as unrecoverable memory errors. So to talk about the types of maskable interrupt, so if the interrupts that can be ignored by the CPU before the execution of critical instruction sequence, those instructions comes under your maskable interrupts. So maskable interrupts are the interrupts that can be ignored by the CPU. Suppose if any critical instruction that has to be executed, so those critical instructions will be given higher priority by the operating system to be executed, and the lower priority interrupts can be masked. And moving on to the storage structure, we'll be talking about the random access memory, your main memory, the hard disk, you call it as a secondary memory. And as we all know that your RAM is volatile and your secondary memory is non-volatile. Volatile in the sense, so if the power is switched off, the contents in the RAM will be erased. Whereas in the non-volatile memory, the contents cannot be erased even after the power is switched off. Then about the memory hierarchy, we'll be talking about the memory hierarchy here. So here, the lower level, you have the magnetic tapes, optical disks, the magnetic disk. So above which you have solid state disk, the main memory, cache on the registers. So when you just look into the memory capacity of the magnetic tape, it is low when compared to the higher level memory registers. So moving up the hierarchy, the capacity and the throughput is higher. The accessibility and the capacity is higher. That's what. So to talk about the design constraints, so what is the size of the memory? What is the speed of the memory, and how much expensive the memory is? So how much is the size? How fast the memory is for accessing the data, and how expensive, whether it is costly or it is not costly. So all those comes under the design constraints. And moving on to the characteristic of memory, we have capacity with respect to the access time and with respect to the cost. Faster the access time. If the access time is faster, then the greater cost per bit. The greater the capacity, smaller cost per bit, and greater capacity, slower access speed. So yeah, the faster access time, greater cost per bit. So they are directly, the access time is fast means they are directly proportional to the cost per bit. Capacity and the cost per bit, they are inversely proportional. That is, greater the capacity, smaller cost per bit. Greater the capacity, slower access speed. So these are all the some of the characteristic of memory with respect to capacity, with respect to the access time, with respect to the cost. So accessibility of register is more than the cache, and the accessibility of cache is more than the main memory, and so on. And the size of the magnetic tape compared to the registers, they are higher. About the cache memory, so the main issue is the processor will be executing at a faster speed when we compare to the access time in the memory. So the solution is we go for the cache memory. Its size is small, access time is fast. So as I told you, in the memory hierarchy, the lower down memory thing, which is your magnetic tape, the capacity is more, but the access time is less when compared to registers. So similar way in cache, the size is small, but the access time is fast. So the cache is a memory which is be located between the main memory and the processor. So it is given in the diagram. So word is being transferred between the CPU and the cache. Word is nothing but a 8-bit block transfer between the cache and the main memory, as it is all the frequently accessed data will be stored in the cache in order to improve the throughput, because the cache has got the faster access time. So blocks of data will be transferred between the cache and the main memory. So 8-bit is nothing but a word. The block here, nothing but a double word. So all that comes under the block. Then how do you perform read operation? It is depicted in this flowchart. So receive the address, read address from the processor is the block containing the read address in cache. Then fetch the read address word and deliver to the CPU. If no, access the main memory for a block containing the read address. Allocate cache slot for the main memory block. So first, to start with, receive the read address from the CPU. So is the block containing read address in cache? First, we have to check whether the read address, the address is present in the cache or not. Whether a particular block of data is present in the cache. If it is present, then we have to fetch the particular word and deliver to the CPU. If it is not present in the cache, we have to access the particular block of data from the main memory containing the read address and allocate a cache slot for the main memory block. Then after allocating the slot, we'll be loading the main memory block into the cache slot and deliver the array word to the CPU. So if the block containing array is present in the cache, we'll fetch that and deliver to the CPU. If not, we have to just allocate a slot in the slot for the main, allocate a cache slot for the main memory block, then load the memory block into the cache slot. So this is how the read operation will be carried out in the cache memory. Then moving on to the input-output structure. So here, generally after setting up the buffer, the pointers and the counters for the input-output device, the device controller will transfer an entire block of data directly to or from the device and the main memory without the intervention of the CPU. So that is what is being given in the diagram about the input-output structure. So one interrupt will be generated for per block. The device driver, then the yes. So one interrupt will be generated per block, and it will be given to the device driver. That is without the intervention of CPU, block of data will be transferred between the device and the memory. So that is what is being given in the diagram. So here the CPU will be executing its own instruction. Meanwhile, parallelly, the transfer of data, that is direct memory access. Direct memory access means without the intervention of CPU, The blocks of data will be transferred between the device and the memory. So once when the DMA is going on, parallelly, CPU will be held in executing the other instructions. So this is about your input-output structure. So while the device controller is performing these operations, the CPU is held with the other device in order to accomplish the other task. So this is about the input-output structure.